The negative is not in the brackets, it's with the y. We agree?
Yes.
And if our y's are negated, the positives become negatives and the negative y's become positive. So what axis are we reflecting on? The x. If the negative is with the x, it affects the x, correct? So if it's positive, it becomes negative, and negative it becomes positive becomes negative becomes
Positive.
what axis are we flipping around?
The Y.
The y. Okay, so let's look at this one here. It says the graph of y equals f of x is shown. So in grade 11, most people, if they didn't understand transformations, were still like, I'm good at this. Because what they did is they typed into their calculator and they saw what happened. And then they would state that with a lack of complete knowledge of what the transformation actually did. Okay? The problem is this year, they'll give you a graph that doesn't actually have an equation that pertains to it. So can you actually type into your calculator and look at it? No, you have to sketch it. So if we look at A is y equals negative f of x. In transformations in words, what transformation is happening? Does that could be negative y's or negative x's? Negative y's. What happens when we have negative y's? Reflection in the x-axis. What's my mapping? XY becomes, yeah, it's not with the x, right? So it's not going to, mapping, whatever in the x affects the x, whatever's not in the x affects the y, so it's going to be x negative y. And now we can apply it to the graph. Remember, the graph's just more than one coordinate. When it applies to coordinates, we use mapping. So I'm going to do blue for this one. Where are the invariant points going to be on? The x-axis, the mirror. Remember, I put my toothbrush against the mirror and you all thought I was an idiot, but at least the only part that didn't reflect was the toothbrush on the mirror. The mirror of the reflection of the x-axis is this. Now, on a test, people will tell me there's two invariant points because they're drawn to the bolded points. But this, like these lines, are just really, really tight little tiny, tiny points, correct? Like if you're just drawing a whole bunch of little points and then you're connecting them, you don't even realize you're doing that. So the whole graph has a ton of coordinates on it, does it not? So people will tell me there's two invariant points, but is there actually only two? No, there's three. That's also an invariant point. Don't just get drawn to the bolded points, right? Down that x-axis, there's still a point. So we have other points on here. So this one's going to stay the same. Then we have 1, 2, 3, 4, negative 4, and 1, 2, 3, 4, 5, 6. So negative 4, 6 is going to become negative 4, negative 6. And then I connect them. And I have negative 1, 6. It's going to become negative 1, negative 6. Connect them. Then I have this one, 1, 2, 3, 4, negative 3 is going to become 4 and positive 3. And then I have this one stay. You guys try this one. So if we do this one in, let's say, red, I have y equals f negative x. So all my negative x's will become positive, and all my positives will become negative, so I'm reflecting in the x-axis. I mean the y. I don't know why I said x. It's always the opposite axis of what it's affecting. So if it's affecting the x's, it's going to rotate about the y. If it's affecting the y, it's going to rotate about the x, right? Now it's with the x, so my mapping is going to be xy becomes negative xy. And I only have one invariant point. It's right here. Okay, so I start again. I'm going to use negative 4, 6. But it's going to become negative and negative 4. So 4 and 6. I don't know why I skipped this one. 1, 2, 3, 4, 5, 6. Negative 6 is 0. You become 6, 0. Those are connected. Then I have negative 1, 6. It's going to become minus and minus. So 1, 6. That's through here. And then I have 4 and negative 3. It's going to become negative 4 and negative 3. And my last one I have is 7, 0. It's going to become negative 7, 0. We're going to look at example 6 then. Example 6 just says determine where the reflection is on. So if we look at example 6, it says a graph drawn in the thick line is a reflection of the graph drawn in the thin line. So the thin line is the original, the thick line is the transformed graph. So here we need to write the equation of the graph of the thick line. So let's say this one is f of x, and this one is f of x, the thin line. Go away. Is this one reflecting in the x-axis or the y-axis? Where's the invariant point landing on? The x-axis. Remember, if wherever your invariant point lands is where the mirror is, correct? So that one is reflecting on the x. So if it's a reflection in the x-axis, what's actually being negated? The y's. So it's not going to be, it's going to be y equals negative f of x. What about b? Where is it reflecting? Because that's where the invariant is, right? So what is being negated? The x values. So it's going to be f of negative x. So you're writing the new equation after these have happened. So try out 7a and 7b. If there's a reflection in the y-axis, what becomes negated in that equation? If there's a reflection in the x-axis, what becomes negated here? Try it out. So with these ones, bless you, because there's no f's in them, you can type this into your y1, type the new equation you came up with into your y2, and if we're looking for a reflection in the y-axis, we're looking for invariant points on the y-axis, correct? It should be crossing on the y-axis at the same spot. And if we have the square root of x as a reflection in the x-axis, it should be the same thing. This is why Windows can't be open for you. Who else is doing it? Taisei? I mean Tazy? It has to be a new calculator in order to do it, because the old ones don't do it. Oh, I think it's not by choice. I think she's doing it by accident. Okay, you stop. Mackenzie, it's not by choice. Your calculator's just doing that, and they are ADDing. Like if I threw a feather in here, you guys would be done. I just throw a feather in the air and get no math learning. Just Put a squirrel in here, we wouldn't even know what to do. It's not you, it's Sydney's window. Your window's fine. You don't need to close it. You just need to. Can't. All right. So write the equation of the image of a reflection in the y-axis. So if we're reflecting in the y-axis, we're going like this. What's being negated? X's. So I'm going to go to my x and I'm going to make it negative. If I type this one into the original and this one into the, y1, this one into y2, I'm going to actually have the intersections of both graphs on the reflection on the y-axis, right? So then you can double check it. So remember, if they don't have f's in them, you can actually type them into your calculator and look at them. Now this one is a reflection in the x-axis, so I think about it. It's down here, it's up here, it's down here, it's up here. What's being negated? My y's, right? My x's would stay the same, my y's would be negated. So if I wanted to negate my y, I negate all of my y's. So I actually put a bracket, a negative in front of the function, correct? This function happens to not have any more actual terms, so it would be y equals negative root x. All good. But what if the actual function was this? If you're someone who puts just a negative in front of the x, you're going to get this question wrong. Because remember, in all the other ones, we negated the whole function. We negated f of x, correct? Well, we have to negate the whole function, yes? So if I was doing this to this function, I would have to go y equals negate the whole function. And so I would get negative root x plus 3. Whereas if it's a reflection in the y, it only affects the x. But if I gave you this as my original, say it was y equals x squared plus 3x, there's more x's than just one, correct? So every x has to be negated, every x, if it's a reflection in the y. So I would get y equals negative x squared plus 3 times negative x. So it would be x squared minus 3x. So when it's a negative, or a reflection in the y-axis, every x has to be negated if there's more than one. Okay, then we're going to flip over. So we're just going to look at this. It says, we're not going to draw the graph, we're just going to finish these up. So it says, given y equals x squared plus 1, determine the equation of the reflection in the y, determine the equation of the reflection in the x. So you do the equations. Go. Reflection in the y-axis means it affects the what? The x's. So all my x's will be negated. There happens to only be one. So I'm going to take my x, rip it off my page, and replace it with a negative x squared. Wait a second, it's the exact same equation. How is that possible? Well, this graph is actually this. If I reflect that in the y, what happens? It's the exact same graph. How many invariant points are there? Trick question. People will tell me all. It's not all, but there's not all. Remember, an invariant point definition is a coordinate that did not change. So how many are there? Yeah. One. This is the only one that doesn't change, correct? This arm over here is going to become this arm, and this arm over here is going to become this arm. So the only invariant point is actually this one. But the graph did stay the same ultimately in the end, right? But the arm swapped. So it's still only one invariant, but people will tell me it's all invariants. So. Okay? What about so your equation will stay the exact same if it's symmetrical about the axis you're reflecting on, right? Okay. What about this one? Well, this one, we have to negate the whole function if it's a reflection in the y. So we get y equals negative x squared plus 1. So we get y equals negative x squared minus 1. I'm giving you 10 minutes for this, and then we're moving on to stretches. So if you work quickly, you should finish your homework. And then we're moving on to stretches. So I will give you till 10:45, then we're going on. Just like reflections end up multiplying your x's and y's by -1, stretches multiply your x's and y's by the number that happens. So here we find out that there are things called horizontal stretches and vertical stretches, which is the last transformation we have to do. Tomorrow we're putting them all together. So vertical stretches are in the form y equals a f of x, and a stretches the graph vertically by a factor of a. So here we have this a in front. Well, the way that you have to write it out is you have to say it's a vertical stretch by a factor of a, or 2 or 3 or whatever the number is. In this case it's an a, about the x-axis. So if it affects the y, it's still about the x-axis. Just like if it is a negative, it's a reflection in the x-axis. Now some people say, well, I can just write half of that, right? No. You have to write the whole thing or you don't get the marks. So it's a vertical stretch by a factor of a about the x-axis.
What is like about the x-axis?
It's stretching it about the x. So if the x is down here and you're stretching your y values, it's going to get wider or narrower about the x-axis because your y's are going to go this way, right? So if your y was at 1, it's now at 2. If your y is at -2, it's now at -4, let's say. So it's stretching it about the x-axis, just like it would reflect it in the x-axis. So anything that affects y's is always about the x. Anything that affects x is always about the y. Because if you're stretching your x's, you're going to stretch them on opposite sides of the y-axis as well. So the point xy becomes xay, and the points on the x-axis are invariant. If a has a negative sign, that doesn't mean it reflects at all. If a has a negative sign, that means, or sorry, it doesn't mean it stretches. If a is a negative sign, that's that reflection. Okay? So we're going to look at example 1. We're going to describe this one. So we have to describe the transformations that happen here. Do you see how there's a -4 in front? Do you see that? What does the -1 do? We just went over it. It's a reflection in the x-axis. We agree? Cool. The 4 is going to be a stretch. Your stretch is never negative because the negative doesn't stretch it. The negative reflects. We always have to do our transformations in SRT. SRT. That's the form we have to do them in. Stretch, reflect, translate, because it's order of operations. If they give them to you, when you state them, you always have to state them in order of operations. SRT. So, do we have any stretches here? Yes, the moment we have a 4 in front, we have a stretch, correct? So we say it's a vertical stretch, no short form. Vertical stretch by a factor of 4. You don't say -4. The negative is not a stretch. The negative is a reflection. And what axis is our vertical stuff about? About the what? X-axis. So the 4 gets us a stretch. The negative gets us a what? Reflection in the which axis? What would my mapping be then? XY becomes X. Instead of just -y, it's actually going to be what this time? And what's my A? -4y. So stretches and reflections multiplied by the variable, translations add and subtract to the variable. Okay, then we're going to flip over. Example 2 says, given the graph of f of x, once again, they just gave us an f of x graph, not with an equation. Use a table of values to sketch 2 f of x, or we could just use mapping, right? So what is our mapping going to be when there's that 2 in front? xy becomes what? X. It's going to affect the y because it's not with the x. What are we going to do with it? 2y. So we're going to have our original xy, so we have negative 2, 0. And then I put in my mapping. Negative 2, 0, and then I'm going to get negative 2, and then 2 times 0. So it's negative 2, 0. It stayed the same. Because just like with reflections, these are going to remain invariant. Because you're multiplying 0 by something, correct? When you're multiplying 0 by something, it stays the same. So just like reflections in the x-axis, stretches in the x-axis remain invariant. Then we have other coordinates. So we have negative 1, 2. It's going to become negative 1 and then 2 times 2. So I get negative 1, 4. Connect. And then I have 0, 5. Is going to become 0 and 2 times 5, which is 0, 10. I'll pretend that's straight. Oh my goodness, it's getting worse than this. So when we move graphs, we use mapping. If you can't fill your mapping in right, though, from off the equation, you're in trouble. And we're going to do example 3. Example 3 says graph y equals x squared. So we're going to do that first. Y equals x squared. You could type it into your calculator, right? So type in y equals x squared. It's your base, it's your parent function of the x squared graph from grade 11. And you could press graph and see what it looks like. It looks like it has a minimum on 0, 0, right? So I can go second table, second graph, and it tells me it's 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Now remember, we have to say x scale 1, y scale 1. You have to say what the scale is so that I know what each of the ticks are, right? Or else it's an assumption that they're 1. We don't want to assume. Now you could do a table of values. You could plug 0 in for x, so you'd get 0 squared is 0, plug 1 in for x, 1 squared is 1, 2 in for x, 2 squared is 4, and that's how they're getting the table, right? You're taught that in grade 10, how to do t-tables. So it's rounded at the bottom. It's not a perfect point. It's not a mountain. And then we go up and curve. Now here's a replacement notation. It says replace y with 3y. So my equation is y equals x squared. And it tells me to replace y with 3y. Remember, replacement is like replacing a tire. You go to the tire, you take the tire off completely, you throw it away, and you replace the tire with a new one, right? You don't keep the previous tire. That would be 2 tires in one spot. You literally can't do it. You would just not be driving your car. So same thing with replacing y's. So I take this y off the board, I huck it across the room, and I replace it with a 3y. And the rest stays the same. Am I in the right form to be able to say the vertical stretch right now? No, I have to get into y equals. How do I get the y by itself? Divide by 3. And instead of writing divide by 3, I need to have something in front of my x squared so that I get my stretch. Dividing by 3 is the same as multiplying by what? What's in front of this x squared currently? A 1. So we can write this as 1/3 instead of dividing by 3. It's the same thing. Now some people will say, is it with the x or is it in front, Mrs. Lepp? I don't know. If it's with the x, what does it need to be? In the brackets with the x. Is it in the brackets with the x? Was there even a bracket? No. What happened is your x has a bracket like this. So it still has a bracket like that. So it still has a bracket like that. So that's not a horizontal stretch, right? That is a vertical. So we say vertical stretch by a factor of what? How many? 1/3. About the? I touched the board somehow. I don't even know what just happened. About the x-axis. My mapping is going to be x, y becomes x stays the same because nothing happens to my x. What happens to my y? What do I get? 1/3 y. So all my y's are being thirded, multiplied by 1/3. So this one here is at -2, 4. It's going to become -2, and then 4 times 1/3. I don't know why I put the bracket there. -2, and then 4 times 1/3. Or 1/3 times 4. So I get -2 and 4/3. 4/3 is 1.33333. So I'm now at -2 and 1.333. I'm here now. Then I can do -1, 1. Is going to become -1, and then 1/3 times 1, which is just -1 and 1/3. So it's 0.33333. This one's invariant. And then because you're quadratic symmetrical, this is going to go down to 1/3. This is going to go down to 1.333. And we get this graph. So actually, if we have a really small stretch factor, it makes the graph wider. If we have a really large stretch factor, it's going to make my y's grow really fast. So it's actually going to make it look narrower. And we're flipping over to horizontal stretches. Remember how horizontal translations were the opposite? So if it was x plus 3, we actually went 3 to the left, right? And if it was x minus 3, we actually went 3 to the right. Horizontal stretches are flipped. So if you have a 2 in front of an x, it's horizontally stretched by the reciprocal, which is a half. If you have like a 2/3 in front of your x, it'll be 3/2. The horizontal stretch always flips. So, in talking about horizontal stretches, here it says, if horizontal stretches are in the form of y equals b to the x, then b stretches the graph by 1 over b. Because this would be b over 1, wouldn't it? Any numbers just over 1, you can put any number over 1, 7 over 1. Any number is actually a fraction, like the number 4 can be a 4 over 1. It can be a fraction too, right? So if it's b, then it would be b over 1. So your horizontal stretch always flips from equation to words and mapping. Equation. And I'm putting a double-headed arrow on here because it's in both directions. Equation to words and mapping. Because words and mapping are the same thing. It flips. It's called the reciprocal. So equation to words and mapping with translations, like horizontal translations, right? It flipped. Did the opposite. If it was x plus 3, I went 3 to the left. If it was x minus 3, I went 3 to the right. Horizontal stretches from equation towards a mapping flip, reciprocal. So this one has y equals 5x. Well, I know it's with the x, so it affects the x. We agree? So if I go to do mapping right away, I know I'm going to get xy becomes something x comma y. What's the something that goes in front of the x? Is it a 5? What always happens from equation towards a mapping? It's reciprocal. So currently in equation it's 5 over 1. What's it going to be in mapping in words? 1 over 5, 1/5. So this is a horizontal stretch. By a factor of, remember words in mapping are the same. What number did I use in mapping? 1/5, correct? What number am I going to use in words? 1/5. Whatever number you use in one, you use in the other. So I use 1/5, I'm going to use 1/5. About the y-axis. So this one, we're given the graph of y equals f of x. Sketch the graph of y equals f of 2x. So it's with the x, so it's a horizontal stretch. We agree? It's a horizontal stretch. By a factor of what? Yeah. 1/2 about the y-axis. The horizontal stretch always flips. So if I used a half in my words, I'm going to use a half in my mapping. Mapping and words are the same. xy becomes 1/2 xy. Now what's going to remain invariant is your y-axis again. Because I have 0, 5. Watch. If I go 0, 5, and then I go 1/2 of 0, comma 5, a half times 0 is just 0, 5, right? So this is my invariant. Then I still have to apply my others. So I have -2, 0. I'm going to get -2, 0, bless you. Becomes 1/2 times -2, comma 0. 1/2 times -2 is -1. So now it's at -1, 0. So it's squished in, right? It's taking my x's and halving them all. Halving all my x's. So the next one is at 1, 2. -1, 2, sorry. It's going to become 1/2 of -1 and 2. Half of -1 is -0.5 or -1/2 and 2. So it's halving. And what's it halving about? The y-axis. You see that? So that's why it's in the about the y-axis. And then our last one is 4, 0. Now I'm going to have 1/2 of 4, comma 0, which is 2, 0. So it also half to that. When you're done that, we're going to flip way to example 8. I'm not going to make you do the harder ones here. Example 8. So, remember how I told you we can go from equation to words and mapping? Remember we can go from words and mapping to equation as well? So, does my vertical stretch ever flip? Did my vertical stretch number ever flip? No, if it was a 2, it was a 2 in equation, it was a 2 in mapping, it was a 2 in words. Correct? What's the only one that flips? Horizontal. Mapping and equation, or mapping and words, does it switch? Mapping and words are the same in a heart, right? Mapping and words, if I use a 2 in mapping, I use a 2 in words. Where does it flip? When it goes to the equation, correct? Or if it comes from the equation to those two, it flips. So, here I have, write the replacement for x or y and write the equation of the image. I just want the equation. So if I have a horizontal stretch by a factor of 6, about the x-axis, about the y-axis. If I do mapping, let's do mapping right away, just let's practice. What would my mapping be? It's horizontal, so it affects the what? The x. So I'm going to get something x comma y. It's a factor of 6. What am I going to have there? Mapping and words. Mapping and words are in a heart. 6. Mapping and words are in a heart, correct? So if in mapping it's a 6, in words it's a 6. In mapping it's a 6, in words it's a 6. Mapping and words are the exact same thing, just different. Words are the way to explain it. Mapping is the way to move coordinates. They're the same thing though. So if I have a 6 in words, I have a 6 in mapping. You're going to learn to appreciate vertical stretches because nothing, they just always stay the same. So vertical stretch, let's do mapping. We'll come back and do equation in a second. Vertical stretch by a factor of 1/5. It affects my x or my y. Vertical. Does it affect my x or my y? Vertical is your y. So I'm going to get something y. What's great about vertical? Stays the same. Equation, words, mapping, right? So if it's 1/5, it's 1/5 in the equation. It's 1/5 in words, it's 1/5 in mapping. Verticals are the best. Their translations are always what they are. Their stretches are always what they are. Horizontals are the flippers. Okay? Here we have a reflection in the x-axis. Which one does that affect, x or y? It's y, because it's opposite axis, right? So I know I'm going to have x, y becomes something x comma something y. Well, my something y is for sure going to be negative because it's a reflection in the x-axis, so I know I'm going to get a negative. If it was just a reflection in the x-axis, I'd be done. Weirdly looking, but done. Then here we have a vertical stretch. Which does that affect? Vertical stretch. Verticals are always y's. Vertical stretches, vertical translations. Vertical stretch about the x-axis by a factor of 3. What number do I put in with the y? 3. Verticals never switch. D, we have a horizontal stretch, so we do mapping. Horizontal stretch affects the x or the y. Horizontal. X. Now we're going from words to mapping. Words to mapping are in a heart. Words to mapping are in a heart. So does the number change? Words and mapping are the exact same way of explaining the exact same thing, correct? So if it's a horizontal stretch by a factor of a half, I get a half x. Vertical stretch by a factor of a quarter y. Words and mapping are the exact same. Do not overthink words and mapping. They're the same way of expressing something, right? Okay, So now we have words and mapping, which are the exact same. Do you see how the numbers did not change whatsoever in any of these? Because words and mapping are the same thing, correct? When we go to the equation, though, from words and mapping, horizontal will switch. From words and mapping to equation, horizontal will switch. So if I go back to A is a horizontal stretch factor. So if my original is y equals f of x, my horizontal is going to be y equals f. I'm going from words and mapping to equation. It will flip every time. So if it's 6, it's going to be 1/6. Why is vertical amazing? Stays the same through everything. Equation, words, mapping, always stays the same. Okay? So we have a vertical stretch by a factor of 1/5. Cool. 1/5 goes in front of my f of x. Next one is vertical as well. It's a reflection in the x-axis and a vertical factor of 3. I've multiplied by -1/3. Do you see this? -3, sorry. Do you see that? I'm just going to multiply by -3 again. Because verticals rock. Nothing changes. Now D. We have a horizontal stretch by a half. I'm going from words and mapping to equation. So instead of it being 1/2 x, what's it going to be? 2x. And then I have a vertical stretch by a quarter. Verticals never change. Verticals never change. So we'll do a little summary for ourselves here. We're going to go vertical. Oh, thank you, board. What the heck? They flip. So vertical stretches flip, they become, horizontal stretches flip, they become reciprocals, correct? Horizontal translations go the opposite direction of what the sign is. So if it's positive, it goes right, if it's negative, it goes left. The only thing with horizontal that doesn't flip is a reflection, because a reflection is just a negative sign. It's a negative sign and it stays a negative sign. Okay? So your homework for this one, I'm just going to assign a few questions. You have to get practicing them. Like I said, if you don't practice every night, what happens? I'm going to put them all together tomorrow. And if you don't know when you keep a horizontal stretch and flip a horizontal stretch, it's going to be ugly. Like, not kind of ugly. Your head will just be like, poof, and exploded. So you have to get this down before tomorrow. Practice, practice, practice. I could say it'll be so easy, don't worry about it, but I'd be lying. You have to know when you keep, when you change, when you keep, when you change. So it's the same page. If you're someone who's like, I know I need practice, you can always come and schedule help, and I can throw questions on the board, and you have to tell me what's transformation, what's the equation, what's the mapping. You just practice till it's stuck in your head. Because if you're still going, change, horizontal, vertical, that's a scary test. Like, that's not even like a slightly scary test. That's like, good. Because I will have every option of an oopsie there, right? So I'm going to have the option of a half. I'm also going to have the option of 2 every single time. I'll have this one and this one every single time. And you might be like, well, that's mean. No, that's just the answers. I'm not going to put like a half negative 17, smiley face, and purple. Like, you'd be like, oh, it doesn't actually make no sense in saving it, right? So it's not going to happen. Tomorrow we get them all together. So all we have left actually is one lesson in transformations. It's inverses. So tomorrow and Friday, I'm literally just throwing a whole bunch of questions at you, and we're going to try and keep going through them. Throw questions, do go through them. Throw questions, go through them. With all the transformations together. Then on Monday, you learn inverses. Okay? So over your break, I'm going to give you the hand-in so you can work on all the questions but the inverses. I'll tell you which ones you can work on. And you're like, but I want to take the whole week off. Sure. Scary. Because you're going to have a test when you come back. But it's going to be.